So let's work a few examples. And before we get into that, let's talk a little bit about what is the difference between doing three-phase and single-phase transformer calculations. And the definitions are basically the same if we're talking about things like percent voltage regulation, or if we're talking about doing like efficiency calculations. They're going to be similar, but the big thing you need to watch out for is that when you have rated kVA and you have rated kV, because we're talking about three-phase transformers, and this rated kVA is a three-phase value, this rated kVA is a line value, that when you're getting current, you have to use a factor of a square root of 3. Kind of what's going on here is if you're trying to calculate a phase current that you've got a three-phase power, you divide this through by 3 to get a single phase. If you got a line value voltage, you divide this by a square root of 3 to get this aligned to neutral value. And in this process, the 3 cancels out with a factor of a square root of 3. And so this gives us in the denominator this calculation, this square root of 3 factor. That's really the big thing that trips up most folks. If we convert this all into per unit, we don't run into this, and sometimes we'll be working this in per unit, but just kind of watch out for this. So efficiency calculation is basically the same. You can still talk about doing a percent voltage regulation, but just watch out when calculating actual currents to watch out for this factor of a square root of 3. So power base, when we're working in per unit, this will be a three-phase value now. The base voltages on the primary and secondary side will be line voltages. And then when we calculate a base current, similarly, again, we got to have this factor of square root of 3 in the denominator. For Z base, we don't need to worry about the square root of 3, because if we're doing a V base times V base divided by S base, the square root of 3 times square root of 3 cancels out with the 3 in the denominator for the base calculation. So let's take a look at an example where I've got a three-phase transformer connected up 4,160 volts line on the high side, primary side, 480 volts on the secondary side, rated at 2,500 kVA. So this is a decent size industrial transformer. And we're supplying a load operating at 2,000 kVA at 0.9 power factor, and we're told that the secondary side is at 460 volts. And a lot of these problems, I'm going to give you the secondary side voltage, and we're going to work backwards to the primary side. Now, if we had a power flow, we're going to go in the opposite direction. But generally for these things by hand, we're going to start with the secondary voltage assumed. And we're told the transformer parameters are such that I have an equivalent resistance of 0.9% and equivalent reactance of 5.7%. So this is where we'd go to the table to get these values if we didn't have these values. And so for this particular three-phase load, what I'm going to do is I want to determine what's the secondary line current. I'm going to refer this to the high side, to the primary side. We'll go ahead and neglect the excitation current because it's not going to add too much to that. And then I'm going to figure out how much primary side voltage do I need in order to get 460 volts at the load. And then if you're told that this efficiency is 96%, which we've seen before is not a very good value anymore, but on old transformers, this is what we probably have. What would be the total core loss? So for working this through, we're going to go ahead and we're going to calculate, some base values, which we're going to use later on. What I'm going to have is I'm going to have a primary voltage of 4160 for rated. All right, so that's going to be my base on the high side. 480 volts is a rating on the secondary side, so that's my base there. And then I'm going to use for my S base the rating of the transformer to 2500 kVA. So as far as the base primary side current, which is the same as rated current, by the way, S base divided by square root of 3 times V base on the primary side, when I substitute in the numbers, is going to give me 347 amps. On the secondary side, I do that same calculation, except I use the base voltage on the secondary side, which is going to give me a rated current of 3007 amperes. Okay, so 3007 amperes is a pretty good size current because we step the voltage down, and when we step the voltage down, then the rated current values have to go up to compensate. So these base values of current are also going to be the same as the rated currents. Now, if I have a certain loading condition, and say I want to start off by calculating the actual current, then I take the three-phase power for the load, I divide by square root of 3 times the line voltage. And if I've got a 2000 kVA load, I divide through by square root of 3 times the actual voltage of 460, I'm going to get a magnitude of 2510 amps. For the angle, what I'm going to do is I'm going to take minus the arc cosine of the power factor. Now in this problem statement, note that I said this was lagging. And so this means that the current has to lag the voltage, and that's where the minus sign comes from. And if I take the arc cosine of the power factor, this gives me minus 25.8 degrees. And so this is with respect to the reference voltage for phase A to neutral being 0 degrees, obviously. So the magnitude of the current I have on the secondary side is 2510 amps. Now, let's suppose I want to convert this over to the high side. How do I do this? One way you could do this is you could take this actual current, you could divide through by the base, get this in per unit, and since the primary and the secondary side per unit currents are the same, then you can multiply this by the base on the primary side, and that would be one way you can do it. The other way you can do this is you could simply use what's called the effective turns ratio of the transformer. So the effective turns ratio of the transformer is basically going to be the ratio between the high side and the low side. And so in this case, what you're going to have is N effective is going to be the 4160 divided by the 480. And if you then have the current on the secondary side, what you can do is you can divide through by N effective. And what that will do is that will give you the high side current. And so when I apply this ratio, then what I can do is I can actually transform the secondary side current into the primary side current. And what you should see is if I'm going from the secondary to the primary side, if voltage goes up, current's got to go down. They've got to go in the opposite direction. Okay, so if you want to just simply see the relationship between a secondary side phase current and a primary side phase current, you could use what's called this effective turns ratio. It doesn't make any difference if it's the delta Y connection or Y delta connection or Y or delta delta. This is always going to work. So now let's go ahead, for the sake of doing the voltage calculation, let's convert into per unit. So I'm going to take the actual current and I'm going to divide through by the base current on the secondary side. And that's going to give me 0.835 per unit for the current with this same angle. And what I can do then, if I want to go ahead and figure out, well, what's going to be this primary side voltage, I could take the secondary side voltage and I can add to it the drop across the transformer. This is going to be R plus JX times the secondary current per unit. One thing I have to watch out for is I don't have rated voltage on the secondary side. It's not 1 per unit. So I take the actual voltage, divide through by the base value, and then what I'm going to do is I'm going to add to that the Z times I, which is the drop across the transformer. And what I see is on the high side, I'm going to have 0.987 per unit and an angle of 2.3 degrees with respect to the secondary side. And so on the primary side, if I take this 0.987 and multiply by the base of 4160, then I have 4104 for the required primary side voltage. So note in this case that we're slightly below rated because we got an actual low voltage across the secondary side. For doing the efficiency related calculation, basically what we're told in this case is we're told what the efficiency is, and we have to work backwards and calculate the no load loss. And so power output is S out times power factor. So that's 2000 kVA times the power factor 0.9. So this is the real power output. The copper losses are given by I squared R. So this would be the current in per unit squared times the resistance in per unit, 0.009. Note that this multiplied out would give me a per unit value. If I want to get this in terms of watts, I have to multiply by S base. And so this is 2,500 times 10 to the third, which gives me an actual copper loss of 15.7 times 10 to the third watts. And since I know that my power input is related to power output by the efficiency, and if power input in this particular case right here is going to be power out divided by efficiency, then the power in is this particular number here. And then the core loss is basically power in minus the power out minus the P copper that I just calculated, where this core loss turns out to be 59.3 kilowatts. Normally, if we're operating at full load conditions, normally what we would see is we'd see these values for copper loss and core loss being about the same for usually an optimal type of transformer design. But we're not operating at rated output in this particular case right here. And then also these numbers are a little bit rounded out. But anyway, this is one type of calculation you can do. You can actually work backwards and you can actually figure out what the core loss would have to be. All right, so here's another example where we're going to consider a delta Y type of connection. And what we're going to do is we're going to look at an imbalance case. And normally, if you're trying to do an imbalance analysis, you can't really use conventional three-phase per unit analysis for this. You have to kind of break it down, look at the details of the transformer connection. So this is what we're going to do here. So for this particular delta Y connection, this is the way this is actually connected up. This is how we're connecting up transformers 1, 2, and 3. And know what we're getting is we're using 208 volts on the secondary side in this case for the rated value, which gives us 120 volts line to neutral. So in the problem statement, we're supplying this from 12.47 kV source. All right, so we've got a rating of 12.47 kV line on the high side. And then the transformer secondary side is set up for a 120/208. So this means that we have 208 volts line, 120 volts line to neutral. And this is going to be giving us a grounded secondary circuit. We're going to hook up a 100 kVA load for three-phase. That's going to have a power factor of 0.8. And then we're going to have a single-phase load of 25 kVA, and it's going to be at a different power factor of 0.9. So assuming that we're operating at rated voltage on the secondary side, what we're going to do is we're going to work backwards and figure out what we're going to have for the load currents, what's going to be the secondary side phase currents, and what's going to be the primary side phase currents. And then we'll take a look at what's going to be the relative phase shift and what's going to be the kVA loading on the three-phase transformers, on the three transformers, assuming that this is constructed out of single-phase transformers. And so anyway, here's the connection. Transformers 1, 2, and 3, power connected up to the primary side voltages, the capital ABC values. And then this shows us on the secondary side where we have the lowercase a, B, and C to represent the secondary connections. So in this particular case, the way we're going to do this is just simply draw the loads into the circuit, and assuming we have rated voltages at the load side, work backwards. And I kind of redrew this to make this easier to see. And so basically note that these are the polarity connections. where we have H1 match up to X1 on the secondary side. This is how the connections would have to be set up. These show you the relative phase relationships. IA on the high side would go into transformer 1, ICs in the middle, IBs on the right-hand side. And for the connecting up the load, I've got this three-phase load connected up at A, B, and C. Note this doesn't make any difference if it's grounded or not, because if it's balanced, there's no neutral current. But then the single-phase load is going to be connected up between A and N. And so the way I'm going to work this is I'm going to get these individual currents for the loads. I'm going to use this to get IA, IC, and IB on the secondary side. These are the line currents. And then I'm going to make use of the fact that IA is related to this single phase transformer current IAC. IC is related to the single phase transformer current ICB. And IB is related to the single phase transformer current IBA. So like I'm going through and I'm just kind of doing this stuff as if I had three single phase transformers, and I'm just kind of going through all the detail of calculating the different currents using the Kirchhoff current law relationships. So if VAN is our reference point on the secondary side, if it's 0 degrees, I've got 120 at angle 0 degrees for VAN. For VBN, this is 120 at angle minus 120, and this is VCN. VCN is going to be 120 at angle plus 120, so this is a balanced three-phase set. The line values of voltage are calculated by taking the differences in the line to ground voltages or line to neutral voltages. So VAB is going to be VAN minus VBN, so this is 208 at 30 degrees. VBC is 208 at angle minus 90, and VCA is 208 and 150 degrees. So for the three-phase load, what I'm going to do is to calculate the contribution to the three-phase load. I'm just going to do this for phase A because phases B and C are just going to lag and lead by 120 degrees. I take the three-phase load, divide by 3, take the complex conjugate of that, and then I take the line to neutral voltage and take the complex conjugate of that. So I is S conjugate divided by V conjugate for the single phase quantities. I got the 100 kVA divided by 3. I've got the angle given by minus the arc cosine of the power factor angle because I've got lagging power factor. Divide through by the voltage, and this gives me a current of 277.8 at minus 36.9 degrees. So I use that, and that basically gives me what the phase B and the C phase magnitudes are. And I just subtract off 120 degrees to get the phase B value, add 120 degrees to get the phase C value. Now for the single phase load, that's 25 kVA, that's hooked up to phase A. And so I take this 25 kVA, I divide through by 120, take the complex conjugate of the power, that's minus the arc cosine of 0.9 in this case. And this gives me a current of 208.3 at an angle minus 25.8 degrees. Now to get the net phase A current, I take the contribution of the three phase and the single phase, add those two up, this gives me 483.9 at minus 32.1 degrees. For getting phase B and C, since that doesn't involve the single phase load, I just simply had what I calculated from the three phase load. And know what we have in this case is we have an imbalanced set of currents, all right? So imbalanced current here, and you have same values for phases B and C, but you have a higher value of current for phase A. And this is what you'd get in real life, is you're gonna get these imbalanced currents. Now we're not gonna do a voltage drop calculation because that's kind of tricky in this case, but what we are gonna do is we're gonna translate these to the primary side. So what I'm gonna do is, since I'm working with the individual transformers now, instead of using the effective turns ratio, I use the actual turns ratio of the single phase transformer. So per phase, when I have those three single phase transformers rated 12,470 volts on the high side and 120 volts on the low side. And this has an actual turns ratio of 103.9. And so where I have IA, IC, and IB on the secondary side, if I divide by the actual turns ratio, then what I'm going to get is what these single phase transformer currents are on the high side. And then I make use of the fact that IA, the line current, is IAC minus IBA using Kirchhoff's current law. And if I substitute in, this gives me 6.6 amps at minus 12.3 degrees. Similarly, I can calculate the phase current IB and IC. Again, I use Kirchhoff's current law with the actual primary side currents on the single phase transformers. And again, what I see is I see an imbalanced three-phase set. So anyway, if you have imbalanced load on the secondary side, obviously you're going to get imbalanced load on the primary side. Now, if VAB is 208 at 30 degrees, then I could also use the actual turns ratio to translate these values to the high side. I get VBA, I get, so which is going to be actual turns ratio times VBN, because I get a value right here. VAB is going to be minus VBA. And one thing I want you to note in this case is if you're going to relate VAB on the high side to VAB on the secondary side, right here, know what we're seeing is we're seeing a 30-degree phase shift. And this is what we get when we have different connection types on the primary and the secondary side of the transformer. Okay, so anyway, what we're seeing is we're seeing a 30-degree phase shift in this particular case here, which is what we would expect to see. So then if you're going to go through and you're going to calculate the power on each single phase transformer, you can take voltage times the current. What's kind of interesting is that the first transformer has to carry 58 kVA, where transformers 2 and 3 just have to carry 33. And so basically, if you have an imbalanced load, it puts more stress on one or maybe two of the transformers than the third one. They don't carry all the same load in this case if it's an imbalanced sort of load. So anyway, this just kind of shows you the difficulty of going through an imbalanced analysis. Most of the time when we're going to be analyzing large-scale distribution circuits, we don't know exactly how the loads actually connected up, the single-phase loads connected up. So when we do large-scale power system analysis, we just usually assume that all loads balance, kind of more like the example one. But if you had a certain industrial commercial situation, you were concerned about maybe overloading a transformer, this is what you would have to do if you really wanted to kind of look at substantial imbalance in the load. Okay, so I'm going to go ahead and stop here, and then the last video, I'll kind of show you how we can verify example one using a computer program. And I'm going to kind of show you this stuff online as well, rather than kind of pulling up MillSoft right here. On the online session, we'll go through, how we can actually manipulate MillSoft rather than me just kind of showing you the screenshots.